Hello everyone, welcome to the class. So today we are just going to study about dielectrics. What are the different types of dielectrics and why I should study dielectric. Okay. So dielectric is a one type of insulator, first point. So as it is an insulator, so it will not have any of the free electrons. So whenever we'll just place the dielectric in an electric field, what will happen and how it is different from the conductor. We'll study today why the concept of electric field is introduced here. Because the capacitor is useless if it is not connected to the supply voltage. Whenever it is connected to any of the supply voltage, then it can hold some charges for a very small amount of time, depending on the dielectric material you have used. But obviously you will think that dielectric is a one type of insulator, so why should I use in the capacitor? I should use some conductor. But what will happen whenever you are using a conductor and how the dielectric will give you the benefit? Today we'll learn this topic. So we'll just make two columns. In one column we'll learn about dielectric, in another column we'll learn about a conductor, how they are different actually. So let me just make the heading of that. So in a conductor, what are the properties we know? That I have already told you, that the conductor can conduct the electricity. That means it is having lot of free electrons. So that's why whenever the electricity or the heat wants to travel through this, they can easily pass through them because there is a very lesser resistance they have. So if you see the cross-sectional area of a conductor, so this is the cross-sectional area we are just making here. Okay. In the conductor there are a lot of free electrons. Initially they are just moving like that. They are not aligned with respect to any of the directions. And there are the positively charged ions. And there are positively charged nucleus are also there, which are fixed at some particular point. Positively charged particles, they are not able to move. They are just fixed with the lattice. Okay. I hope you guys are studying the chapter of solid state, right? So you know what is the lattice and what is the structure and so on. So here in the conductor there are a lot of free electrons and the electrons are free to move. But the positive charges, that means I'm talking about the nucleus, they are fixed with respect to the lattice. They are not movable. Okay. Now, whenever the conductor is placed in an electric field, so what will happen? I'm just making the diagram again thus you can understand. So this is my conductor. Whenever I'm just placing the conductor in an electric field, now the electric field should be applied externally. So this is an external electric field. It is represented as E naught. Okay, this is the direction of external electric field. Oh, I will not give the vector sign over here. So whenever the electric field is applied in the conductor, so let me just draw it here so it looks beautiful, no? So in the electric field the conductor is placed. So due to the application of electric field, what do we know? That inside of the conductor there are a lot of free electrons. So whenever a charged particle is placed in an electric field, obviously due to the presence of electric field it will experience some force, right? And look at the direction of the electric field. It is just showing from left to right. So obviously this kind of electric field will obtain due to a positive charge, right? So all of the negative charges, that means all of the electrons, will be aligned to the extreme left surface. Because of the force of attraction, all of the negative charges will be present in the extreme left surface of the conductor. And the positively charged nucleus, they are not able to move. But if the lattice arrangement changes, so obviously all of the positive charges, due to the force of repulsion, they will just move away. right? So this is an arrangement we are just looking here. So as you can see, whenever the positive and negative charges are separated by some distance, so inside the conductor there some electric field is induced. And what is the direction of electric field? Remember one thing, electric field should always have a direction from positive to negative. So inside the conductor, the electric field should be having this direction, and it should be named as, there is an induced electric field. That means whenever the conductor was placed in an external electric field, all the positive and negative charges are forced to be arranged in that way. So that's why, due to the presence of opposite charges, as they are separated by a small distance, there will exist some electric field, and this electric field is known as induced electric field. Why I am saying induced? Because due to the external electric field, that electric field inside the conductor, it is being induced. So look at the diagram. External electric field is having the direction from left to right, but the induced electric field is having the direction from right to left. So both are opposite. So what will happen? They will cancel out each other. So we can say one thing, that E naught plus of induced electric field, their summation, that is equals to 0. They will cancel out each other because they are equal and opposite with respect to each other. So we can say their summation will be equals to 0. This is all the cases about the conductor. But dielectric is different. As I have already said, dielectric is a one type of insulator, right? So the number of free electrons are not present here. Okay. So let me just draw the diagram of the initial arrangement of the dielectric. Actually, there are two kind of dielectrics you will learn. One is a polar dielectric, another is a non-polar dielectric. So at this time, as I have not told you what is polar, what is non-polar, I'm just drawing the diagram of a non-polar dielectric. Okay, let me just tell you at first, otherwise you will not understand what is a polar and what is non-polar. Okay, then it will be more easy to understand. So the dielectrics are classified as polar and non-polar. So what is a non-polar dielectric? Let me give you some example, and we are moving to chemistry. Now you know the arrangements of H2, Cl2 or CO2. That kind of molecules are known as non-polar molecules, or they behave as a non-polar dielectric. Why? If we see the diagram of H2, it looks like that. Now there are the two hydrogen atoms. This is one hydrogen atom, this is another hydrogen atom. Their centers are coinciding with respect to each other. Okay, their centers are coinciding with respect to each other. If we see the diagram of Cl2, then they looks like this. They are the two chlorine atoms. There is a Cl, this is another Cl. Now their centers are coinciding with respect to each other. Right? So this kind of molecules are known as non-polar molecules, and they don't have any dipole moment. Now if we just look at the diagram of CO2, okay, I'm just making the diagram of CO2, but not according to the chemistry. Actually, we just want to say that the polar and the non-polar dielectric materials, they are being differentiated with respect to their arrangement. Okay, in the non-polar molecules, you will see the arrangement that they are symmetric in nature. Their arrangement is very much symmetric, their structure is symmetric in nature. Even if I just draw the diagram of CO2, you will understand. Suppose this is your O, C, O. Now this is your CO2. So in this case, if you see the arrangement, that all of the molecules, the center of all the molecules, they are just aligned in one line. So that's why we can say that their arrangements are very much symmetrical with respect to their structures, and initially the molecules are not separated with respect to each other. So they are not having any kind of permanent dipole moment. Okay. And what about the polar molecules? The polar molecules are already looked like that. Like if we just see the example of HCl, so one kind of ionic molecule we can say. Otherwise H2O, if you see the diagram, if you see the arrangement of molecules in HCl, so if this is the chlorine atom, and if this is the small hydrogen atom, you can say, then their centers are separated, right? Their centers are separated. We can say that they are not coinciding with each other. We can say that their centers can coincide, otherwise they cannot coincide also. Now in this structure you can say that the centers of positive and negative charges, they are being separated with respect to some distance, right? So actually we know that hydrogen is positive and chlorine is negative in nature, and in this diagram they are separated with some greater distance with respect to the non-polar molecules. The non-polar molecule centers are coinciding with respect to each other. Okay, the very small distance, very small separation, you can say. Actually the arrangement is like suppose you have one book, then you have placed another book which are parallel with respect to each other. Then in that case, if you just make them very much close, then you can say that two of the books are coinciding with respect to each other. So that kind of arrangement is having in non-polar molecules. I'm not able to make that diagrams because they are separated distance between their centers that is very much small. But if you see the polar molecules, there is some considerable distances between the positive and negative charges, and these are ionic in nature. If you see the diagram of H2O, so it will look like that. This is the oxygen, this is hydrogen, this is another hydrogen. So let me just write it down. Now if you see that their arrangement is like that, their centers are separated by some distance, and one molecule is positive, another molecule is negative. So whenever two equal and opposite charges are separated by some small distance, it forms a dipole. So that's why the polar molecules have permanent dipole moment. Permanent dipole moment. Okay, and the non-molar molecules, they don't have a permanent dipole moment. We just have to understand that whenever the polar and the non-polar molecules will be placed in the electric field, you can say in the external electric field, then what will happen for the polar molecules, for the non-polar molecules, right? As their structures are different, their properties are different. Now we are just going to study them. So at first we should study with the non-polar molecules, okay, who don't have any permanent dipole moment. So let me just give the heading non-polar molecule. Now I hope you are getting some of the noises, right? The outside noises are coming. Actually my home is just beside of the GT road, so that's why the cars, trucks, buses are going on, and that's why some noises are there. Now in a non-polar molecule, if you see the arrangement of different molecules in a dielectric slab, that means it is having some cross-sectional area of A, and here we'll just represent their arrangement. So for the case of non-polar molecule, they just like that, they appears to be like that, right? As they are not being separated, they are coinciding with each other, and they are having very small distance between their centers. Actually, they are not being separated so much. So this is the arrangement of a non-polar molecule in the absence of external electric field. So whenever external electric field is absent, so E naught will be equals to 0, right? Now, if we place the dielectric slab in the electric field, then what will happen? So this is our dielectric slab, and here if we just place in the external electric field of E naught, this is our external electric field. So due to the application of external electric field, some force will be experienced by the charged particles, and they will be separated. They will be separated in that way that all of the negative charges will be arranged in the extreme left hand side, and all of the positive charges will be arranged in the extreme right side. The positive charge particles, again I am telling, they are not able to move. There is some rearrangement of their lattice structure that is being happened. Now whenever they are being separated with some distance, so obviously we can say inside this dielectric, non-polar dielectric material, there will exist some induced electric field. That induced electric field will have a direction like this, right? We can say this is our induced electric field, and this should have some dipole moment also. So due to the application of the electric field, whenever the molecules are arranged in such a way that they are behaving like a dipole, so this thing is known as polarization. Okay, due to the polarization we are getting an induced electric field. The induced electric field is in the opposite direction of external electric field, and in this case their summation, that means E naught plus of E induced, that is not equals to 0, because induced electric field will be less than of external electric field. So that's why it will reduce the effect of external electric field. Okay, suppose what happens that in Markham there is lot of cold, right? Now we have to wear the sweaters, jackets and so on. Now whenever we are just wearing the sweaters, jackets, mufflers and so on, now the effect of the cold, that is reduced. The same thing is happening here. Due to the polarization of the charged particles, we can say the induced electric field is reducing the effect of external electric field, and their summation is not equals to 0. So you can say that after the application of electric field, the non-polar molecule have some dipole moment. Initially they don't have a dipole moment, but after the application of electric field they have some dipole moment. Okay. Now if we discuss about the dipole moment, can you say that what should be the direction of the dipole moment? Now we know that thing, that for a dipole, the dipole moment acts from negative charges towards the positive charges, right? So there are a lot of negative charges and positive charges are placed like that. So they will have the dipole moment in the same direction of the external electric field. So we can say that the dipole moment should be in this direction, and due to the arrangement of the molecules, there should have a net dipole moment in the same direction of external electric field. Up to that much, whether you have understood. If you have any of the single doubt, please inform me. Don't keep quiet. In our area, I am just trying to get a whiteboard. In opposite of my house, there is a coaching center as well. But at this COVID situation, they are closed and they are not allowing someone else to use their whiteboard. So that's why I'm not getting that one. I will just try to install that OBX Studio, thus you can see my face and the reactions as well. Now, thus I can make this thing little bit interesting. Now we are just moving to understand the polar molecule. Now let me just give the heading of polar molecule. So, polar molecule, right? So the polar molecule, they are having the arrangement like that. This is the dielectric slab of a polar molecule. And inside the slab, they are having the arrangement like that. That means the positive and negative charges are separated by some distance. So this is an arrangement of the dielectric slab of a polar molecule. So you can see that the positive and negative charges, they are already separated with some small distance. So initially they are having some permanent dipole moment. Okay. So whenever you will place that dielectric slab in an electric field, what will happen? Let's see. At first we have to make the diagram. So I'm just separating that. I'm just making the diagram over here. Now in the presence of electric field, that means this is our E naught, right? This is the direction by which E naught is working. So whenever you will place the dielectric slab in the electric field, obviously the electric field will apply some force on these charges and they will be separated in that way. All of the negative charges will be at the extreme left and all of the positive charges will be on the extreme right. So why this happening that every time I'm just placing the polar or non-polar molecule in the electric field and they are just arranging that the positive and negative charges are being separated more and they are just behaving like a dipole and they are having some net dipole moment because the look at the direction of the electric field, it is just coming from the left side towards the right side. So this is due to the positive charge. So whenever the electric field, the external electric field is applying on this dielectric slab, so all the negative charges will be attracted more because the electric field is due to a positive charge. So that's why all the negative charges are arranged in the extreme left and all of the positive charges will be repulsed. So that's why they will shift it towards the extreme right. Okay. And now this polar molecule will have a permanent. So now the polar molecule will have a net dipole moment and we can say that inside of this polar molecule there should have some induced electric field in this direction. That induced electric field will reduce the effect of external electric field and the summation of E naught plus of A induced, that is not equals to 0. So in both of the cases one thing is seen, that whenever you are placing that polar or non-polar molecule inside of an electric field, they are just arranging in such a way that they are having some induced electric field that is reducing the effect of external electric field. Even they are having a net dipole moment. The dipole moment is acting from the negative charge towards the positive charge, like that. From the negative charge towards the positive charge, the dipole moment P will act. The net dipole moment per unit volume is actually known as a polarization. Okay. Why the polarization is happening? Because you are placing that dielectric slab in the electric field. That's why the arrangement happens and you are getting some polarization. So we can say that the polarization should have some relation with the electric field, right? As we can say that how much more intense will be the electric field, more the polarization will happen. So the polarization will be directly proportional with the external electric field E or E naught, you can say. So we can say polarization P, that is equals to X E multiplied by of E. So what is Xe here? It is not the variable like in your mathematics. So it is actually the susceptibility of the medium. Susceptibility means with the application of the electric field, how much the molecules will be polarized, that Xe is a measure. Now the polarization P is having a formula also. If we can see that the area of this dielectric slab is A, we are assuming that the area of this dielectric slab is A, the length of the dielectric slab is L, and it is having a surface charge density. As you can see that after the arrangement, if we see the extreme left portion, then that much portion should have some surface charge density. Due to the negative charges, it should have a surface charge density as minus of sigma. Due to the positive charges, it should have the surface charge density as plus sigma, right? So how the polarization should be represented? That means polarization means amount of dipole moment per unit volume. So how the dipole moment is actually represented? That is the charges present multiplied by the length. In this case we are not assuming 2L, only the length is represented as L, divided by the volume, right? Now this thing should be modified. As we know that the surface charge density sigma is equals to charge present per unit area, right? If you see the extreme left portion, how much negative charges are present per unit area, that is the surface charge density minus sigma. So we can say that Q is equals to sigma multiplied by of A. Okay, in this case we are using the mod value, so that's why I'm not writing the negative or positive sign. So Q is equals to sigma into A into of L divided by a volume. Volume is equals to, we are having the formula that area multiplied by of length. So we can say that the polarization is equals to how much? The area, the length, they are getting cancelled out and we are getting only surface charge density. So you can say the extent of polarization is directly equals to the surface charge density of the dielectric slab. Now it will be more better that it should be represented as plus minus of sigma. Okay, finally you can write it down, it will be more precise. Okay, so revise the total completed portion. In the next day we'll just study about the parallel plate capacitor and what are the different arrangements can be made with the help of a capacitor. But say that whether the total thing that we have just covered in this, whether it is understandable or not, or in which part you have the doubt. Okay, now thank you so much, study well.